Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to continue our lecture on work and energy, and we've made it to the second objective, which is titled work. Now to start, work is not energy, but a measure of energy transfer. In fact, there are only two forms of energy transfer, work and heat. In physics, work is the energy transferred to or from an object via the application of force along a displacement. So whenever a force is applied to an object, causing it to move, work is done on the object. This relationship is mathematically expressed as the dot product between the force vector and the displacement vector, and it expands into f d cosine theta, where F is the magnitude of the force applied, D is the displacement of the object, and theta is the angle between the force and the direction of displacement. Now, to better understand this equation, let's break down the terms involved. Force is any interaction that, when unopposed, changes the motion of an object. It can be a push or a pull acting on that object. Displacement is the distance moved by the object in the direction of the force applied. And the term cosine theta in the equation accounts for the direction of the force relative to the direction of the displacement. So when the force is applied in the same direction as the displacement, theta is equal to 0, and cosine 0 is equal to 1, and the work done is going to be maximized. Now let's apply the concept of work to systems involving gases, where work is often related to changes in pressure and volume. So imagine a gas trapped in a cylinder with a movable piston. The gas can do work on the piston as it expands, or the piston can do work on the gas as it compresses. The work done in these processes is described using the equation that work is equal to pressure multiplied by change in volume. So W here is the work done by or on the gas, P is the pressure of the gas, delta V is the change in volume of the gas. And again, when the piston compresses the gas, work is done on the system, and when the piston expands, work is done by the system. Now, this relationship between pressure and volume, it can be visualized using a pressure-volume diagram. On this diagram, pressure is plotted on the y-axis, and volume is plotted on the x-axis. Now, the area under the curve on a pressure-volume diagram, this represents the work done by or on the system. So, for instance, just to repeat, during the compression of a gas, when the piston moves inward, the volume decreases and the work is done on the system, which typically results in a work that is less than 0. On the other hand, during the expansion of a gas, when the piston moves outward, the volume increases and the work is done by the system, resulting in work value that is greater than 0. Now, if you want a more in-depth explanation of this, I just want to quickly point you to my MCAT General Chemistry playlist. In the video where we discuss gases, I believe that is chapter 8, where it's titled The Gas Phase. There is more of a breakdown regarding this. But with that, we're going to move into discussing power next. Power is the rate at which work is performed. Power tells us how quickly work is done, and it's defined by the equation P equals W over delta T, where P is power, W is the work done, and delta T is the time over which the work is performed. Now, power is a crucial concept because it not only tells us how much work is done, but also how fast it is accomplished. So for instance, if two engines perform the same amount of work, the one that does it in less time delivers more power. Now let's build on our understanding of work by exploring the work-energy theorem. This important principle connects the concepts of work and kinetic energy, and it gives us a really powerful tool for analyzing motion. The work-energy theorem, it states that the net work done on an object is equal to the change in its kinetic energy. So mathematically, it's expressed using this equation right here, where W net is the net work done on the object, delta K is the change in kinetic energy, and this change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy. To understand this theorem, consider that when work is done on an object, it either speeds up or slows down, depending on the direction of the force relative to its motion. This change in speed corresponds to a change in the object's kinetic energy. So for instance, if a force is applied to a stationary object, causing it to move, then the work done on the object is converted into kinetic energy. And the work-energy theorem is incredibly useful because it allows us to analyze the effects of forces on an object's motion without needing to know the details of the force or the path taken. As long as you know the initial and final speeds, we can determine the net work done on the object. So to just kind of wrap up, we've discussed work and the expression that describes work. It is the dot product between force and displacement, which can be expanded as force multiplied by displacement multiplied by cosine theta, where theta is going to be the angle between the force and the direction of displacement. Then we discussed our pressure volume diagram and how the area under the curve on a pressure volume diagram represents the work done by or on the system. Then we defined power. This is the rate at which work is performed, and this is the equation that describes it. Power is equal to work divided by the time over which the work is performed, which, by the way, is also equal to the change in energy over time. And then we discussed the work-energy theorem, which is a powerful expression of the relationship between work and energy. So with that, let's go ahead and tackle a practice problem. This example says a lead ball of mass 0.125 kilograms is thrown straight up in the air with an initial velocity of 30 meters per second. Assuming no air resistance, find the work done by the force of gravity by the time the ball is at its maximum height. Now, the answer to this problem can be calculated using kinematics and then determining the maximum height of the ball, but it's actually going to be a lot simpler to calculate by just using the work-energy theorem. And the work-energy theorem says that the net work done on an object is equal to the change in kinetic energy. So this is final kinetic energy minus initial kinetic energy. Now, for this problem, we're throwing the ball up, it's reaching its maximum height. At its maximum height is where we're going to be calculating the final kinetic energy. Now, final kinetic energy is equal to 1/2 mv final squared. The velocity at that maximum height is going to be equal to 0. So this whole term is going to be equal to 0. So then what we have is 0 minus initial kinetic energy. This is equal to 0 minus 1/2 mv initial squared. And we have all the information to just plug it in. So it's going to be 0 minus 1/2 multiplied by the mass, which is 0.125 kilograms. Now we can rewrite this in fraction form so that it's easier to multiply with 1/2. 0.125 kilograms is equal to 1/8 kilograms. And then this is multiplied by the initial velocity squared, which is 30 meters per second squared. So what we have here is negative 1/16 multiplied by 900, and I should write kilograms here to keep the units in place, 900 meters squared per second squared. Now, I'm going to approximate 16 to 15 so that the calculation's a little bit easier. Now we have negative 900 divided by 15 kilograms times meters squared over second squared. And this is going to give us a value of, I'm going to write it right here, of about negative 60 joules. So the answer here is going to be negative 60 joules. This is the work done by the force of gravity by the time the ball is at its maximum height. Beautiful. Let's move on to our last and final objective, which is going to be about mechanical advantage. The concept of mechanical advantage is a key principle in mechanics that allows us to understand how machines can make tasks easier. Mechanical advantage refers to the factor by which a machine multiplies the force that's applied to it, and it allows us to accomplish a task with less effort. For a given quantity of work, any device that allows work to be performed with a smaller applied force is said to provide a mechanical advantage. And the basic idea is that a machine can change the magnitude and direction of the input force, and that makes it easier to perform the same amount of work. Now, mechanical advantage is mathematically defined as the ratio of the magnitude of the force exerted on an object by a machine to the magnitude of the force that's actually applied to the machine. So mechanical advantage is equal to the output force over the input force. Now, to further understand mechanical advantage, let's look at simple machines. These are basic devices that alter the direction or magnitude of a force. And there are 6 classical types of simple machines. We'll start with the lever. This is a rigid bar that rotates around a fixed point called the fulcrum, and the lever allows a smaller input force to lift a heavier load by increasing the distance over which the force is applied. Then we have the pulley. This is a wheel on an axle or shaft that's designed to support movement and change the direction of force applied to a rope or a cable. Using a system of pulleys can significantly reduce the input force needed to lift a load, and that's how it provides a mechanical advantage. Then we have the wedge. Now, this is a device that is thick at one end and then it tapers to a thin edge at the other end, and it's used to split, cut, or divide an object by essentially applying forces to the thicker end. And the mechanical advantage of a wedge is determined by the ratio of the length of the slope to its width. Screw is another simple machine. This is essentially an inclined plane wrapped around a cylinder. So a screw converts rotational force, torque, into linear force. The mechanical advantage here depends on the spacing of the threads. Closer threads provide greater mechanical advantage, but they require more turns. The wheel is next. This simple machine consists of a wheel attached to a smaller axle so that these two parts rotate together. Now, a larger wheel means a smaller input force is needed to turn the axle, providing a mechanical advantage this way. And then last, we have inclined planes. This is a flat surface that's tilted at an angle, and it's used to help lift a heavy object by spreading the lifting force over a longer distance. And the mechanical advantage here is calculated by the ratio of the length of the incline to the height lifted. Now, keeping all this in mind, let's go ahead and tackle an example problem. This example says a block weighing 100 newtons is pushed up a frictionless incline over a distance of 20 meters to a height of 10 meters as shown below. Find A, the minimum force required to push the block, B, the work done by the force, and then C, the force required and the work done by the force if the block were simply lifted vertically 10 meters. Now, the first thing we want to do is we want to look at our sketch and determine what forces are acting on this block. Of course, we have our gravitational force acting downward. We also have the force that we're pushing this box towards. We're pushing it kind of upward, this incline. And then we have our normal force, which is perpendicular to the surface of the incline. Now, the minimum force needed to push the block is a force that's going to push the block with no acceleration parallel to the surface of the incline. So this means that the magnitude of the applied force is actually going to equal the parallel component of gravity. So if we resolve our gravitational force into its parallel and perpendicular components, the minimum force needed is a force that's going to push this block, again, with no acceleration, parallel to the surface of the incline. And that means that the magnitude of the applied force, the magnitude, is equal to that of the parallel component of gravity. Now, how do we calculate the parallel component of gravity? It's going to be equal to mg sine theta. Now, mg represents the weight of the object, which we're told in this problem that it is equal to 100 newtons. So mg is equal to 100 newtons. Now, what about sine theta? We can use some trigonometry here. Sine theta is the ratio of the length of the opposite side to the hypotenuse, which is just going to be 10 over 20. So here, this is going to be equal to 100 newtons multiplied by 10 over 20. And this is going to give us 50 newtons. So the minimum force required to push the block is 50 newtons. What about part B? Part B asks us for the work done by the force. Now, work is defined as force multiplied by distance cosine theta. Now, force, we just calculated, is equal to 50 newtons. D is displacement. All right, D is displacement. We're moving it up the incline, total of 20 meters. And then cosine theta here, well, let's think about this. Because the force and displacement vectors are parallel, then theta here is just equal to 0. And cosine of 0 degrees is equal to 1. So now we have 50 multiplied by 20 multiplied by 1. This is equal to 1,000 joules. So that's part B. This is the work done by the force. Now, what about part C? In part C, we're asked, what is the force required and the work done by the force if the block were simply lifted vertically 10 meters? Now, to raise the block vertically, an upward force equal to the object's weight, which is 100 newtons, would have to be generated, and the work done by the lifting force is going to be equal to, again, FD cosine theta. The force is equal to 100 newtons. That's the weight of the block. All right, and then for a distance of 10 meters vertically, cosine theta. Here again, theta is going to be equal to 0 because the force and displacement vectors are parallel. So cosine theta, cosine 0 degrees is equal to 1. And this is going to be 100 multiplied by 10, which is 1,000 joules. So the same amount of work is required in both cases, but twice the force is needed to raise the block vertically compared with pushing it up the incline. Wonderful. Let's continue with our lecture and talk about pulleys a little bit more. Again, pulleys are simple machines that use wheels and a rope to change the direction of a force, making it easier to lift or move heavy objects. In a simple pulley system, a rope is looped around a wheel, and then when you pull down on one end of the rope, the other end lifts the load. The pulley changes the direction of your applied force, and it allows you to exert a downward force to lift something upward. However, it's important to note that this mechanical advantage comes with a trade-off. To gain the advantage of reduced force, you must pull the rope over a greater distance. This is a fundamental principle in mechanical systems. A machine can reduce the force that's needed to accomplish a task, but it usually requires moving a greater distance or applying the force over a longer time. Now, let's go ahead and dive into the difference between a single pulley system and a system of pulleys and how these setups can affect the load and effort required to accomplish a task. Now, in a single pulley system, the mechanical advantage is typically 1. This means that the force you exert on the rope, known as the effort, is equal to the force that's applied to lift the object, known as the load. The primary benefit of a single pulley is that it changes the direction of the applied force, making it more convenient to lift objects. For example, instead of lifting a load upward directly, which could be awkward or it could be difficult, you could instead just pull down on the rope, and then the pulley redirects this force to help you lift the load upward. So just to redefine effort and load, effort is the force you apply on the rope. Load is the weight of the object that's being lifted. So for example, if you're lifting a 100 Newton load in a single pulley system, you have to apply 100 Newtons of effort. The pulley doesn't reduce the force needed, it only changes the direction of that force. And this is useful in situations, again, where pulling downward is just easier or more practical than lifting upward. Now, in contrast, a multiple pulley system can significantly increase the mechanical advantage, allowing you to lift heavier objects with less effort. So let's consider a 2-pulley system. In a 2-pulley system, the mechanical advantage is 2. This means that the system effectively doubles the force you apply. So if you need to lift that same 100 Newton load, you only need to exert 50 Newtons of effort. The pulleys distribute the load across 2 segments of the rope, meaning each segment carries a portion of the load, reducing the amount of effort required from you. So in this case, the effort required is half the load, so lifting a 100 Newton load only requires 50 Newtons of effort, even though the total weight of the load being lifted remains 100 Newtons. Now here's the thing. This advantage comes with a trade-off, and that trade-off is that you have to pull the rope a greater distance. In a 2-pulley system, to lift the load by 1 meter, you need to pull 2 meters of rope. And again, this is because while the force is reduced, the work, which is force times distance, remains constant. The mechanical advantage allows you to apply a smaller force, but over a longer distance to accomplish the same amount of work. Now, if we keep adding more pulleys to the system, then the mechanical advantage continues to increase. For example, a 4-pulley system would have a mechanical advantage of 4, meaning the effort needed to lift the load would be 1/4 of the load. So for a 100 Newton load, you would only need to exert 25 Newtons of effort. But remember, you would need to pull 4 meters of rope to lift the load by 1 meter. Now that we've explored how pulley systems can provide mechanical advantage by reducing the effort required to lift a load, it's important to consider another crucial aspect, and that's efficiency. Efficiency is the ratio of the machine's work output to its work input, accounting for these losses. While pulley systems and all simple machines are designed to make tasks easier by reducing the necessary force, they do not always operate perfectly. In an ideal world where no energy is lost, all the work you put into the system, your effort, should be converted directly into useful work, lifting the load. However, in reality, some of the energy is always lost due to non-conservative forces like friction. So to reiterate, efficiency measures how effectively a machine converts the input work the effort applied, into useful output work lifting the load. It's a ratio that compares the work output to the work input, and this can be multiplied by 100%. In an ideal pulley system with 100% efficiency, all the input work should be converted to output work, meaning no energy would be lost to friction or other forces. However, in real pulley systems, the efficiency is usually less than 100% due to these energy losses. And with that, we've completed all the topics for Chapter 2, Work and Energy. I hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.